Hello, in today's presentation I will start with minimization process or minimization as a general problem in digital systems. Let's first recall the voting machine I introduced in the first classroom lecture. As you remember, there were 3 voters, A, B, C, and the result was true or false when at least 2 of 3, or the majority of them, were for or voted for. And the truth table, we started with a description using truth table, is now here presented on the slide. And I also presented a rule, very simple rule, to get the expression for the output function for the y, the overall result of the voting, or in general any function can be found in this way. So what's the algorithm? For each row where you have a 1, you construct the full product containing all the variables, and you put a dash or complement symbol or inversion symbol on these variables which are 0 in this row. So in this case you've got only A 0, so that's why you put a dash only above A. Okay, B and C are 1, so they are in the product without any inversions. So similarly, this row 1 0 1, you've got 0 on B, so B must be with a dash, and C in the last but 1, and in the last one all of them are 1, so no dash above any of the variables. Then you simply add these cases or these full products to get the expression for y. So this was already done in the lecture. And now, as usual in usual common algebra, you can perform or at least try to simplify the expression. Is there any simplified form of the same function, having less products or less dashes or less elements in the sum? And of course, there's a similar thing can be done in our common algebra. So when you find in the expression x plus a, you can replace it by 2x. It is a common algebra. Similarly, in the Boolean algebra, if you've got something like this, please don't make a mistake. I hope you know that it is an x simply, and as a Boolean algebra. Okay, so you can simplify the sum, yes, by a single x if you find it. Let's try do this using axioms and theorems. You already know. Try to manually simplify this expression. I mean this one. Okay, all right. So what we can do is on the basis of this x is equal x plus x, we can add ABC 2 times or 3 times, any times you want. Okay, so let's do it, and let's make use of commutativity axiom. So I will replace the order of the products. Not A, B, C is the first one, plus I will put this ABC, plus in the second row, plus this one, A, not B, C, plus again ABC, because I can do this on this basis. It is a theorem or axiom. It is, of course, theorem. And then let's repeat for the third one. A, B, not C, and again at A, B, C. Okay, that's the same. For now, it is not simplified. But starting from right now, I can make use of distributivity and factorize out BC from the first pair. I will use another color. Okay, let's say a red one. This and this they can be factorized. Okay, so BC is the common, and then you've got not A plus A. Similarly, the second two products I can factorize, and yes, the common is A times C, and inside you've got not B plus B. And in the third row, the common product is AB, part, and inside you've got not C plus C. Okay. I hope you remember what it is equal to. You know, it is simply 1. It is an axiom or theorem. It is axiom. Axiom number 3, defining identity element. Okay, identity element for product is equal to sum A plus not A, element plus its complement. So now we've got BC times 1 plus AC times 1 plus AB times 1 equals. And you recognize complement axiom about the complement. Sorry, about the same, the identity element. It is x times 1 is equal to x. Okay, it is identity element as well, not the complement. This is identity. So BC plus AC plus AB is the final, simplified, minimized version of the same function y. But it is a simpler and it is a less costly, okay, less expensive in terms of electronic elements which will be used to implement this voting machine. Okay, but it was not very simple. Yes, it was not very simple. And that will be using so-called Karnaugh maps. A Karnaugh map give you a simple way to do this minimization or simplification. Okay, graphically rather than manually expressing, manually transforming the expression in Boolean algebra. A, B, and C. You divide the group of inputs into two halves. Of course, if you have an odd number of elements, you've got 2 and 1. If you have 4 elements, you've got 2 and 2, A, B, C, D. And the table, the map will be square. In this case, I have a rectangular map. And be aware of disorder, not in the normal binary code order, but here you've got 1, 1, the last one, and then 1, 0. It is a gray code. Its name is a gray code. The consecutive sequences differ in one binary bit, each other. Okay, this one and this one have only difference here. This one and this one only here, and so on. And if you have a single, you don't need gray code, for single variable. And you put the value. It is a kind of truth table constructed in two-dimensional way. And that is for y, the output from voting machine, and the output is 1 when 2 of them or more voting for. So 1, 1, 1, 3 of them, 2 of them, and 2 of them. And the remaining cases are zeros. It is not more than truth table. But now you must do a Karnaugh map minimization in a simpler form than before, without making any expression transformation. So you find the neighboring cells in this table. The neighboring has a common edge. Okay, common edge. And these are 2 of them. And to get the expression for the 2, okay, instead of having two separate full products as before. You've got 1 and 1 in truth table. You would have in the previous method you would have 2 full products, and now you've got only one product containing only those variables which are the same for the pair, for the group in general. So look at this. A is the same? Not. A is here 0 and here 1. So A will be eliminated from the product. So the result is B, which is 1 for the 2 cells, and C, which is also 1, so without any dashes. And A has been eliminated because this variable has different values. If you find only at least one case when A or any value differ for the group, this variable will be eliminated. Okay, so the next step is to find another group which common edges, and let's say it's this group. From this you've got which one is not stable. B. In this case, B is 1 for this one and 0 for this cell. Okay, so B will be eliminated, and A will be 0, so without the dash, and C is also 0, so without the dash. So instead of longer full products, you've got shorter products containing less variables, because you eliminate these variables which differ for the group, which have different values. And for this, or you can see that A and B are the only variables which are stable for the group. And there are no more groups that can be combined here. So that's done. So Y is simply as before the sum of these products, but these products are simpler, as you can see, than in the previous, and we will prefer this approach. So after finding the truth table, the next step is to minimize. Minimization with expressions manually, manual minimization is quite difficult and time consuming comparing to Karnaugh map. That's why we'll be using Karnaugh map in this course. Karnaugh map has little importance in the real life, in the engineering life. The engineers use different and much more efficient algorithms, but for our course, for academic purposes, the Karnaugh map is very, very attractive. So that's all. Another way you can find the expression for Y is a heuristic. Heuristically, you can draw just from thinking about the problem. So let's start with considering when Y is 1 is 4, the overall output of the voting machine. When A is 4 and B is 4, what about C? C is not important, yes, because if A is 4 and B is 4, C, it's his or her vote, that doesn't matter. So you stop it. Okay. Then the second case is when A is 4 and C is 4. What about B? You don't care about B. Yes, you don't put any B here. Okay, because that's enough for the voting result to have A and C voting for. And the second and the last at the same time case, when you have 2 of them voting for, is a BC. Okay, B and C are 4. What about A? Doesn't matter. No more cases. So you've done it. You've done it without using any calculations in Boolean algebra, any Karnaugh maps. Okay, it is also possible in simple cases. If you think about A and B as symbols as being 4, because you are using so-called positive logic convention. So A is 4 when A is 1. Okay, it's true. So the product will be true if all of the cases are satisfied. So A4, so A1 and B1, and so on. No more cases. You stop it. And you've got the same as in the case of... But in general, Karnaugh maps is simpler, because in many cases it is not very simple to draw just from thinking about the problem, just from your brain, from mind. So thank you.